What we have looked at so far is the use of the CORDIC algorithm in two different modes, that is vectoring mode and rotation mode. But in all of the examples we've looked at a circular rotation, so we've had a point and it's rotated round about in a circle. Now we're going to look at something we can call a linear rotation. Now it's best seen via the simulation here, and after we've looked at the simulation we'll go ahead and compare it to the mathematics. So before we get started, I will return the simulation back to a 0 position. So we're starting off again with our circle. Now we're going to pick an angle. Now the angle again for this example we'll pick will be 30 degrees. So this little angle in here is 30 degrees. And you can see it crosses this circle at an x value is 0.866 and a y value is 0.5. So we've seen this before. So we can say that the value of our initial angle z, 0, is just some value z. In this instance, that value is going to be our 30 degrees. Our initial values for our x0 and y0 are these values x and y, which we'll put in just now. So the initialization value is a vector here which is in pink. The length of this vector here is just the x coordinate of our vector in blue, so it's going to be 0.866. So we start off with a x value, x0 value, which is our value of x, which is just this length here. And the y0 is some value y. Now in this instance here, to keep it simple, we'll make y0 is equal to 0, so that's just the 0 here. So the x0, y0 is just the endpoint of this vector here in pink. Now before we actually run through the simulation, let's have a look and see what this CORDIC algorithm is going to provide. So the final output here are values xn, yn and zn. So we'll start off with the value zn. So this is the final angle for our value z, and the final angle for our value z is 0. So in effect, this blue line here will sit at an angle of 0 degrees once we've gone through the 9 iterations. The value for our xn will just remain at the value x0, which is just the length here, 0.866. Now the interesting thing in this here is the value for our yn. So this is going to be some height here. Now the value for yn is going to be given by y0 plus x0 times z0. So what we have here is a way of multiplying two numbers together. And if we have a value for y0, what we have is a multiply add. So what I've done up here is I've worked out what we expect our answer to be for this multiplication. So our value for yn is going to be the value y0. Now in this instance here, again, we've stated that y0 is just a number 0. So our final answer is just going to be the value for x0 times z0. So the value for x0 is 0.866. Okay, so that's this distance here. And the value for our z0, well, our z0 here is the angle 30 degrees. But of course, when we're multiplying these out, we have to change the degrees into radians. So it's going to be 30 times pi upon 180, which gives us 0.5236. So this CORDIC algorithm is going to multiply these two numbers together. The first number is the x component of our vector in blue here. And the second number is the angle that makes in radians. And that's going to give us number 0.4537. So what we have here is a way of multiplying numbers together. So first of all, let's have a look and see what we mean by a linear rotation. So we're going to rotate this vector here in pink. So I'll go through the first rotation here. Now you'll see here that it rotates by this length here, and you can see this line in white. Now if I was to again rotate it by another angle, you'll see here it actually just goes up in a straight line. And I'll get another angle here, and so on and so forth. So you can see here, as the angle here changes, it maps out a point, and the end point here maps out a line. So in effect what we have here is a rotation that doesn't provide us with a circle. It's a rotation that provides us with a line. And in fact, if we were to rotate the angle all the way around to the quadrant 2 and quadrant 3, we would generate another line over here. So you can see as we rotate all the way around about, we're going to end up with two lines, a line here and a line over here. So this is what we mean by our linear rotation. As we rotate, we do not create a circle, we create a line. Now once we've worked through the CORDIC algorithm, we'll find that the value for our yn, which is up here, is 0.4537. So the final height here will be a value of 0.4537. So you can see here at this instance, the final position that I've picked here is actually the y point is 0.9259. So when we work through our algorithm properly, we will get this value here. So this is our linear CORDIC algorithm in rotation mode. Now we've seen the initialization and the output already, and this is the actual algorithm. So we've got our x to the I plus 1, y to the I plus 1 and z to the I plus 1, and we've got our value for di, which decides whether we rotate clockwise or anti-clockwise, and it's given by these values here. And remember that I runs from a value of 0 all the way up to a value n. Now in our example here, we actually work through 9 iterations, so it goes all the way from 0 up to a value of n is equal to 8. So as we mentioned previously, we keep the x value constant. In our example there, it always remained at 0.866. So we keep that x value constant by introducing a value of 0 here. So we multiply this term here by 0. So if we multiply it by 0, in effect it just disappears. So it means that the x to the I plus 1 is equal to the value x to the I, and it always remains the same. So this ensures that our xi value is the same value throughout all of our iterations. And again, this value here, which remains the same, is then multiplied within this part of the algorithm. Now one thing to note, and it's very easy to miss, is that the interesting thing here is that the value for our angle that we work out, z to the I plus 1, is different from what we have seen previously. So previously what we had for z to the I plus 1 was z to the I minus d to the I, and it was the inverse tan of 2 to the minus I. But now for the linear mode, we get rid of the arc tan, and we've just left with 2 to the minus I. So let's have a little closer look at this. Now you have access to all of the simulations in the resources section. Now we've seen this simulation before. We have our tan function here in brown, and we said we wanted to use a set of angles, and the first set of angles that we decided to use were going to be the values of 45, and then we would half the 45. If you look at the pink one here, it would half the 45 to 22.5, and that was this one here, and then we would go down to 11.25, so we would be halving each time. But then we said that in order to get rid of the tan theta from our rotation matrix, what we decided to do was use a different set of values for tan theta. So remember, the tan theta is up with this axis here, this is theta, and this is tan theta. So we decided to use a set of values for our tan theta, which were 2 to the minus I. So if you look at the ones in blue here, 2 to the minus I gave us a value of 45 degrees. And then the next one down, again in blue here, gave us a value of 26.565, and then 14, and so on and so forth. So we decided to use that set of values for our angles for the rotation because it allowed us to replace the tan theta within the rotation matrix with the simple value 2 to the minus I. Now for our linear rotations, we're still going to be using the same angles here in blue. So we have our 45 degrees, now 26.56 and 14.036. So for all of the linear rotations, we rotate by these angles. But now in order to work out our angle Z, we no longer use arctan 2 to the minus I. We simply use the 2 to the minus I. So the value for our angles to work out our Z values are going to be given by 2 to the minus 0, 2 to the minus 1, and so on and so forth. So these are the lines in white. So 2 to the minus 0 is just a value of 1. And the value of 1 radian is a value of 57.29578 degrees. So that's the first value we're going to be using for our value of our angle Z. And then the next value is going to be half of that, which is the 28.64, which you can see in white. And when we half it again, and again you can see it in white here, and that's this angle here. And you can see as the angle actually gets down towards 0, the value for our rotation angle is very similar or almost exactly equal to the value for our angle Z. So in effect now we've got two sets of angles. We've got a set of angles for the rotation, and we've got a set of angles in order to find the value of our Z. Now it's best seen by the actual example, so let's go ahead and we'll work through the example in the graphical calculator. So I've added the CORDIC algorithm in up here. Now please note here, there's a typo here, that should say 2 to the minus I. Okay. Now, in order to work out the next position, so our first position here is 0.866, 0. So in order to work out this next position, we're going to use the algorithm. So the value x1 is going to be x0 minus, and this whole term here is just 0. So our value for x0 is just the value 0.866. So x1 is again 0.866, it always remains the same. So that's very simple to work out the x value for all of our points. Now the y value, y1 is going to be y0. So y0 is a value initially of 0. So it's going to be 0 plus this value here, which is xi. So the x0, which is again 0.866. So we're going to have our 0.866 times the value of d. Now this is the interesting part here, because the value for our d is determined by the sine of the angle Z. So the sine of this angle here, well the angle here is plus 30 degrees, so the sine of the angle is positive. So if it's positive at zi is greater than 0, then we can say that d is plus 1. So that d0 is a value of plus 1. And then 2 to the minus I, well that's going to be 2 to the minus 0, which is just a value of 1 upon 2 to the 0, which is just a value of 1. So that whole fact there is going to be 0 plus our 0.866 plus the 1 times the 1. So in effect then what's happening here, we're going to end up with another point here, which is 0.866. So the rotation here is in the positive or the anti-clockwise direction. So we're going to rotate this here up to that point. So this is our second pointer point given by x1, y1. Now we work through the same iteration again, and we're going to put these values in for our value of our x1 and y1. Now note here, in order to find the actual value for our angle, we're going to use this z to the I plus 1 is equal to zi minus di 2 to the minus I. So we've used one set of angles here in order to do the rotation of this pink line here. But we're going to use a different set of angles in order to do the rotation of the blue line. So what's going to happen is zi is going to be a value of 30. So we're going to have our 30 and it's minus this value d. Well, we already looked at the d and the d is positive. But it's going to be the angle 2 to the minus I. So 2 to the minus 0 is just the value of 1. So it's going to be an angle of 1, but of course that's in radians. So 1 radian is 57.29578 degrees. So we're going to take this here and we're going to take off 57 degrees. So we take this one and we'll take off 57 degrees from it. So let me do that now. And this is the next position here of our value for z. So this is a thing that can be quite confusing. We're using two sets of angles, one in order to do the rotation of this pink line here, but the second set of angles is used to rotate this blue vector here, which will tend towards a value of 0. So we'll do one more and then we'll have a look at the finished article. So now we've got the value 0.866, 0.866, and it again goes back into the algorithm. Now when we put it back into the algorithm, we'll find that we're going to do the rotation of this here, but the direction of the rotation is going to be given by the sine of this angle here. Now the sine of this angle here is now negative, so if that is a negative value for this angle, the value for d becomes minus 1. So that means what happens is we're going to rotate this here in the opposite direction, so this rotates down in this direction here. So it goes down by the next angle, which is 26.565 degrees. So this is the next point here. Now, of course, this value here is also going to rotate, and this is going to be given by our zi minus di 2 to the minus I. Now, we already know our value for di is minus 1, so it's minus times minus makes it a plus. So we're going to be adding on the next angle here. So the next angle for this one here is going to be given by 2 to the minus 1, so that's a half. So a half in radians is equal to a value of 28.64789 degrees. So again, we're going to now add this on. So we're going to add on 28.64789. So that will take this line to this point here. So let me go ahead and I'll work through the rest of the iterations till we get to the very end. So I've worked through all of the iterations, and you can see that the final value for our vector here, for our z, it's approximately a value of 0. We don't get it exactly. And the final value here for our yn, which is this height here, is given by 0.4565, which is going to be this one here. Sorry. So you can see here that we've approximately equaled the value that we were looking for. So we've got 0.4565, and we can see that the actual value should be somewhere 0.4537. So we're off a little bit, but that's just the approximation. If we were to use a few more iterations, then we would get a number that would be exact to more decimal places. So you can see here, it does actually work. We've got the number here for our yn, 0.456, and we've got the number 0.453. So that's been quite a long video, and there's been quite a lot in it. Now I'll leave you here with this table, and these are the sets of angles that we're using. We use this set of angles in order to rotate the vector, which we've seen in pink, and we use this set of angle here to rotate our vector, which we've seen in blue, which is our initial angle. Now I've also added in the first two iterations here, which you can pause the video if you like, and you can try from this working through and getting step 3 and comparing step 3 to the simulation in the graphical calculator. So to summarise, we can use the linear CORDIC method in order to multiply two numbers together. The first number is the x component of this vector here, which in this instance is 0.866. The second number is the angle here in radians. In this example, it's 0.5236. And when we work through the algorithm, it will multiply these two together and give us this value here. So we have a neat way of multiplying numbers together. That's all for this video. In the next video, we'll look at using the linear method for the CORDIC algorithm, but we'll use it in vectoring mode. And we'll see how we're able to divide two numbers. So thank you for listening. I'll catch you on the next video. Goodbye.